Okay, understanding compound types declaration. As we've seen, a variable consists of a base type and a list of declarators. Each declarator can relate its variable to the base type differently from other declarator in the same definition. Thus, a single definition might have variables of different types. Okay, int, this is a pointer to int, and it is a reference. Many programmers are confused by the interaction between the base type and the type modification that may be part of a declarator. Okay, so this type definition is a part of the declarator. This is uh, a type modifications. So chapter text and are type modifiers. Thus, defining multiple variables. It is common misconception to think that the type modifier applies to all the variables defined in a single statement. Part of the problem arises because we can put white space between the type modifier and the name being declared. Okay. Legal, but might be misleading. Right. We say that this definition might be misleading because it suggests that int star is a type of each variable declared. Yes. Okay. Accept. Despite appearances, the base type of this declaration is int, not int star, and the star modifies the type of p. It says nothing more about any other object might it be declared. Okay. If it says nothing about any other object that might be declared in the same statement. There are two common styles used to define multiple variables with pointers or reference types. The first places the type modifier adjacent to the identifier. Okay. This style emphasizes that variables has the indicated compound type. The second places the type modifier with a type but defines only one variable per statement. This style emphasizes that the declaration defines the compound type. There is no single right way to define pointers or references. The important thing is to choose a style and use it consistently. Right. In this book, we use the first style to place the or with the variable name. Okay, so pointers to pointers. In general, there are no limits to how many type modifiers can be applied to a declarator. When there is more than one modifier, they combine in ways that are logical but not always obvious. Okay, as an example, consider a pointer. A pointer is an object in memory, so like any object, it has an address. Therefore, we can store the address of a pointer in another pointer. We indicate each pointer level by its own star asterisk, that is, we write star for a pointer to a pointer and star for a pointer to a pointer to a pointer and so on. pi is a pointer to an int and ppi is a pointer to a pointer to an int. Just as dereferencing a pointer to an int yields an int, dereferencing a pointer to a pointer yields a pointer. To access the underlying object, we must dereference the original pointer twice. Okay. This program prints a value of IVAL three different ways: normal, with a pointer, and with a pointer to a pointer. Directly, then through a pointer to int, then finally dereferencing PPI twice to get the underlying value of IVAL. References to pointers. A reference is not an object, hence we may not have a pointer to a reference. However, because a pointer is an object, we can define a reference to a pointer. Okay. The easiest way to understand the type of R is to read the definition right to left. the symbol closest to the name of the variable, in this case ampersand in and r, is one of the most is the one that has the most immediate effect on the variable's type. The easiest way to understand the type of R. Hmm. Okay. The easiest way to understand the type of R is to read the definition right to left. So it is a reference to a pointer, right to left. Okay. Uh, read from right to left. So we go int star and R will star and uh, in reference to a pointer. Okay. In this case, the one that has the most immediate effect on the variable's type. Thus, we know that R is a reference. The rest of the declarator determines the type to which R refers. The next symbol star in this case says that the type R refers is a pointer type. Finally, the base type of the declarator is the reference to a pointer of type int. Okay. It can be easier to understand complicated pointer or reference declarator if you read them from right to left. Exercise. Determine the type and values of each. Okay. This is a pointer. It is a simple int. It is a reference to I. Then I is simple. Let me write it. So we'll go IP. What is the name? Okay, IP, right. IP pointer. Um, IP is pointer. I is int and R is a reference. Then we go I is int, IP is pointer, null pointer, or I would say, but it is a pointer, a value, right? Okay, and the values too. IP is a pointer, undefined, undefined value. Int undefined value, and R the ref to okay. I is int with value, undefined, BTR is null BTR. Then we go IP PTR undefined, and IP2 is int with value, undefined. Hmm. Now we are on to const qualifier. Sometimes we want to define a variable. Sometimes we want to define a variable whose value we know cannot be changed. For example, we might want to use a variable to refer to the size of a buffer size. Using a variable makes it easy for us to change the size of the buffer if we decided the original size wasn't what we needed. On the other hand, we'd also like to prevent code from inadvertently giving a new value to the variable we use to represent variable size. We can make a variable unchangeable by defining with the type const. We define the size as a constant. Any attempt to assign to the size is an error. Because we can't change the value of const object after we create it, it must be initialized. As usual, the initializer may be arbitrary, complicated expression, error. Okay. Initialization and const. As we have observed many times, the type of an object defines the operations that can be performed by that object. A const type can use most but not all of the same operations as its non-const version. The one restriction is that we may use only those operations that cannot change an object. So, for example, we can use so for example, we can use a const int in arithmetic expression in exactly the same way as plain non-const int. A const int converts to bool the same way as a plain int, and so on. Among the operations that don't change the value of an object is initialization. When we use an object to initialize another object, it doesn't matter whether either of the object are both consts. Okay. Although Ci is a const int, the value of Ci is an int. The constness of Ci matters only for operations that might change Ci. When we copy Ci to initialize j, we don't care that Ci is a const. Copying an object doesn't change that object. Once the copy is made, the new object has no further access to the original object. Right. By default, const objects are local to a file. When a const object is initialized from a compile time constant, such as in our definition of buff size, the compiler will usually replace use of the variable with its corresponding value during compilation. That is, the compiler will generate code using the value 512 in places that a code uses buff size. To substitute the value for a variable, the compiler has to see the variable's initializer. When we split a program into multiple files, every file that uses the const must have access to its initializer. In order to see the initializer, the variable must be defined in every file that wants to use the variable's value. Okay. To support this usage yet avoid multiple definitions of the same variable, const variables are defined as local to file. When we define a const with the same name in multiple files, it is as we had written definitions for separate variables in each file. Sometimes we have a const variable that we want to share across multiple files, but whose initializer is not a constant expression. In this case, we don't want the compiler to generate a separate variable in each file. Instead, we want the const object to behave like other non-const variable. We want to define the const in one file and declare it in other files that use that object. To define a single instance of const variable, instance, if file.cc defines initialize a const that is accessible to other files, the same buffer size as defined in file. Define and initialize. This program, file1.cc defines and initializes buffer size. Because this declaration includes an initializer, it is as usual a definition. However, because buffer size is const, we must specify extern in order for buffer size to be used in other files. The declaration in file1.h is also extern. In this case, the extern signifies that buffer size is not local to this file and that its definition will occur somewhere else. We share a const object among multiple files, labels as okay, which of the following are legal? Uh, this is not legal. Say not. Let's say int 0. Okay. Can't change set. This is also okay. References to const. As with any other object, we can bind a reference to an object of const type. To do so, we use a reference to const, which is a reference that refers to a const type. Like an ordinary reference, a reference to const type cannot be used to change the object to which the reference is bound. Because we cannot assign directly to CI, we also should not be able to use a reference to change CI. Therefore, the initialization of R2 is an error. If this initialization were legal, we could use R2 to change the value of its underlying object. Terminology. Const references is a reference to a const. C++ programmers tend to abbreviate the phrase reference to const as const reference. This abbreviation makes sense if you remember that it is an abbreviation. Technically speaking, there are no const references. Okay, because this is the type. Okay, this is the sorry, this is the base type. A reference is not an object, so we cannot make a reference itself const. Indeed, because there is no way to make a reference. Indeed, because there is no way to make. Indeed, because there is no way to make a reference refer to a different object. In some sense, all references are const. Whether a reference refers to a const or non-const type affects what we can do with it with the reference, not whether we can alter the binding of the reference itself. Okay. Initialization and references to const. We noted that there are two exceptions to the rule that the type of a reference must match the type of the object to which it refers. The first exception is that we can initialize a reference to const from any expression that can be converted. Okay, then will be converted to that type of the reference. In particular, we can bind a reference to a non-const object. Okay, okay, reference to const because it is basically a value. You can bind a const int to a plain int object. Yeah. The easiest way to understand this difference in initialization rules is to consider what happens when we bind a reference to an object of different type. Double deval. Here, Ri refers to an int. Operation on Ri will be integer operations, but deval is a floating point number, not an integer. To ensure that the object to which Ri is bound is an int, the compiler transforms this code to something like a const. This is a const int temp deval. Create a temporary constant. Okay, so you can point exception to the rule. So the first exception is that we can initialize a reference to const from any expression that can be converted to that type of the reference. Okay, okay. To ensure things like this. In this case, Ri is bound to a temporary object. A temporary object is an unnamed object created to an int. Operations on Ri will be, but deval is a floating point number, not an integer. Okay. A temporary object is an unnamed object created by the compiler when it needs a place to store a result from evaluating an expression. C++ programmers often use the word temporary as an abbreviation for temporary object. Okay, so it uses a temporary object. Now consider what happens if this initialization were allowed but Ri was not const. If Ri weren't const, we could assign to if Ri weren't const, we could assign to Ri. Doing so would change the object to which Ri is bound. That object is a temporary, not deval. Most we could assign to Ri. That object is a temporary, not deval. The programmer who made Ri refer to deval would probably expect that assigning to Ri would change deval. After all, why assign Ri unless the intent is to change the object to which Ri is bound? Because binding a reference to a temporary is almost surely not what the programmer intended. The language makes it illegal. Sorry. Now consider what could happen if this initialization were allowed but Ri was not const. Okay. If Ri weren't const, we could assign to Ri. We could assign to Ri. Important. Doing so would change the object to which Ri is bound. The object is a temporary, not deval. The programmer who made Ri refer to deval would probably expect assigning to Ri would change deval. After all, why assign to Ri unless the intent is to change the object to which Ri is bound? Because binding a reference to a temporary is almost surely not what the programmer intended. The language makes it illegal. Okay, got it. Let me just, this is, at least it's just standard. A reference to const may refer to an object that is not const. It is important to realize that a reference to const restricts only what we can do through the reference. Binding a reference to const to an object says nothing about whether the underlying object itself is const. Because the underlying object might be non-const, it might be changed by other means. Binding R2 to the non-constant is legal. However, we cannot use R2 to change I. Even so, the value in I still might change. We can change I by assigning to it directly or by assigning. Okay, okay. So we cannot other references, but we cannot change it using this. Pointers and const. As with the references, we can define pointers that point to either const and non-const types. Like a reference to const, a pointer to const may not be used to change the object to which the pointer points. Okay. We may store the address of a const object only in a pointer to const. With const. That's into CPR. Nice. In 2.3.2, page 52, we noted we noted that there are two exceptions to the rule that the types of a pointer and the object to which it points must match. The first exception is that we can use a pointer to const to point to a non-const object. Okay. Like a reference to a const, pointer to a const says nothing about whether the object to which the pointer points is const. Defining a pointer as a pointer to const affects only what we can do with the pointer. It is important to remember that there is no guarantee that an object pointed by a pointer to const won't change. It may be helpful to think of pointers and references to const as pointers or references that think they point or refer to const. Const pointers. Okay. So this is the base type. Pointers to const. Const pointer themselves. Unlike references, pointers are objects. Okay. Hence, as with any as with any other object, we can have a pointer that is itself const. Like any other const, like any other okay, but can't change dval through C. You can assign pointer to const, but we cannot change the underlying value. Like any other const object, a const pointer must be initialized, and once initialized, its value, that is the address that it holds, may not be changed. We indicate that the pointer is const by putting const after the star. This placement indicates that it is the pointer, not the pointed to type, that is const. Another point, const pointer, right? Then we have const pointer, const double is a const pointer to a const object. We have const objects to non-const object also. As we saw in the easiest way to understand these declarations is to read them from left to right. Okay. So it is a const pointer to type of const object. Const pointer. Okay. Uh, const int star const c ptr equals end of read it as read it from right to left as const pointer type const int. In this case, the symbol closest to current ERR is const, which means that cur itself will be a const object. The type of that object is formed from the rest of the declarator. Next symbol in the declarator is star, which means is a const pointer. Finally, the base type of should add base type. Okay, it's fine. Which means it's a const pointer. Finally, the base type of the declaration completes the type of area, which is a const pointer to an object of type int. Similarly, PIP is okay, const type double. The fact that a pointer is itself const says nothing about whether we can use the pointer to change the underlying object. Whether we can change the object depends entirely on the type to which the pointer points. Okay. For example, PIP is a const pointer to const. Neither the value of the object addressed by PIP nor the address stored in PIP can be changed. On the other hand, if our address is a plain non-const int, we can use here to change the value of the. Okay, nice. Top level const. As we've seen, a pointer is an object that can point to different objects. As a result, we can talk independently about whether a pointer is const and whether the object to which it can point are const. We use the term top level const to indicate that pointer itself is a const. Okay. When a pointer can point to a const object, we refer to the const as a low level const. Okay. Which of the following initializations are legal? Okay, and not okay. I think I cannot change the literal, so this is and RS not okay. Let me just check once. So servers, that's 2.4.2. Equals 0. This will give me an error. Yes, that's what I thought. Okay, let me see. And R is wrong. Can't bind to literal. We have 10 const int I minus 1 and 0. Okay, okay, okay. Since type of R is const. Right. like constant charge, like 2. That's I2. This is okay. I2 equals I. That is okay. Constant. This is okay. So const pointer to, okay, it's a const pointer. It's a const pointer to const object. It's okay. You just cannot change, but const objects should be pointed by const, not okay. Const, not okay. Let me quickly check. See, I can declare const int I, but new int so const IP equals and or should give an error. Yeah, IP. Oh shit. Let's tell it. Yeah, invalid conversion in constant star. Right. That's what I thought. Um, then we have const and star const and yeah, it can do from. That's okay. And a const reference to a const object must be initialized. Const objects must always be initialized. Right. If I go const int and the const reference are conflicting declaration. So I've already declared. To just quickly comment out these things. Yeah. Const qualifiers cannot be applied to const. I think it can be applied. Const reference. Const qualifiers cannot be applied to type. Okay, so I cannot really do that, right? Okay, so reference to a const, but there are no const references. Okay, f2 const is valid, but there are no const refs. Explain the following definitions. Identify any that are illegal. Const pointer. Should it be initialized? Const pointers. references. Like any other const object, a const pointer must be initialized. Const pointers must be initialized always. Ah, must be always initialized. Okay. Then we have this insta p. Same here. I declare a const pointer, but I cannot really declare it, right? An initialized const pointer. Same here. And okay, a const reference only const reference can bind to const type. This is okay. Pointer itself is not const, but the type that it points to is const. Right. It should be okay because the pointer itself is not const. I don't know. Same here for both. For both. Using the variables in the previous exercise, which of the following assignments are legal? So I see. Yeah. Okay. We do that. P1 stuff and I see. Object. Uh, different types. P2 equals P1. Uh, point to any other as P2 is const. P1 equals P3, P1 and P3. Different types. P3 equals end of IC. P3. Yeah, okay. And IC equals value of P3. Value of IC equals P3. That is yes. Okay. Subjects that it points to. If it points to a valid, it's been initialized. Same for both. regards of initialization. More generally, top level const indicate more generally top level consts indicate that an object itself is const. Top level const can appear in any object type, that is one of the built-in arithmetic types, class type, or a pointer type. With const pointer type, const is, we can change p2. Low level const appears in the base type. Pointer type. Note that pointer types, unlike most other types, can have both top level and low level consts independently. Okay, so this, the distinction between top level and low level consts matters when we copy an object. When we copy an object, top level consts are ignored. Okay. I and Ci. Okay, we are just, well, P2, P2, and P3. It's okay, it can point. Pointed types match. Copying, copying Copying an object doesn't change the copied object. As a result, it is immaterial whether the object copied from or copied into is const. Okay. On the other hand, a low-level const is never ignored. When we copy an object, both objects must have the same low-level const qualification, or there must be a conversion between the types of the two objects. In general, we can convert a non-const to const, but not the other way. P3 has both top level and low level const. When we copy P3, we can ignore its top level const, but not the fact that it points to a const type. Hence, we cannot use P3 to initialize a P2 has const same type. Okay. So we cannot use P2, which points to a plain const. On the other hand, we can assign P3 to P2. Both pointers have the same low level const. The fact that P3 is a const pointer, that is, doesn't matter. Okay. For each of the following declarations, indicate whether the object being declared has top level or low level const. Low level, okay. I'll go low with this. Nothing here. Nothing here as well. P2 low level const, P3 top level const. Where is I? Okay. P2 low, P3 top. Given the declaration in the previous exercise, determine whether the following assignments are legal. Explain how the top level or low level const pointer applies in each case. R1 equals V2. Okay, R1 where R1 is here equals V2. Type mismatch. P1 equals P2, P1 and P2. Again, type match. Type def method. Type def p1 equals p3, p1 p3. Type def p2 equals p1, p2 and p1. Const type can point to this, right? A const type can point to non-const. Can point to non-const. p2 equals p3, p2 3. Can it point to a pointer? Okay. Maybe just let me do this once. Even 4.3, right? Uh, okay, so I declare constant. What is that? Constant v2 equals 0. Here int v1 equals v2. That's okay. Okay, it drops the low level const. Then we have const v2 equals pointing to v2. Same v2 low, v3. Const p3 pointing to I, but there is no I. The const reference R2 is pointing to V2, whichever can. Let me just constant I equals 32. And reference R2 is pointing to, the reference is binded to V2. This works. Now let me try. R1 equals R1 is R1. Did I miss anything? Yes, I did miss indeed. Then we have and star P1 is V1, which it can do, yeah. And reference of R1 equals to V1, which is also valid. There. Then can R1 be into V2? R1 is of type and V2 is of type. It will most likely throw an error. It will say, oh, okay. So R1 is of type int reference and V2 is const. Okay. So simple pointers can point. Okay. In general, we can convert a non-const to const, but not the other way around. This should not R1 equals V2. We say R1 is of type int, right? And V2 is a const int. Any operation. Okay, so I think it points to a temporary variable was 3 make main. Let me then print R1. Okay, let me just print V, right? 0. Okay, so and if I go R1 3. Okay, so type mismatch and it works, but it points to a temp object, right? Because I had just learned about this temp object, right? R again error R4 is plain non-const reference. Okay, initialization and reference to const diva. Listen to it. Because finding a reference to a temporary is almost not surely what the program intended. The language makes it illegal. It's a temporary const int from diva. Okay, that is what is happening here. Okay, P1 and P2 type difference, right? So we'll go with P1 equals P2, which P1 is of type and P2 is of different type. So will it again, but it is only with reference, or is it with as well? P3 is no lower constant, P doesn't. Yeah, go through an error here. Yeah, okay. So I'm right there. And P1 3. I don't think it will work as well. Different types, yes. Okay, const can point to not const. So P2 and P1. Yeah, and P2 equals P3 equals P3. Just but okay, it itself cannot change. All right, so call it.